This is part 2 of section 1. Please make sure that you have watched part 1 before watching this video. What does it take to be classified as a liquid? Well, it has to have a constant volume. However, it takes the shape of its container, which we didn't see solids doing. Particles move faster than they do in solids, and they're able to move past each other, meaning they have the ability to flow. They are fluids, rather than being held in a fixed position. Particles are still closely packed together, which allows attraction between particles. You can see in the jar that the particles in the liquid are not well organized. It may not be easy for you to see that they're in constant motion, but it's definitely visible in the image in the circle. Those particles are moving around. They're not stuck next to the same neighbors all the time. The attractive forces occurring between particles within a liquid is what gives liquids some of their special properties. What types of attraction can occur? Well, there's a cohesive force. This is known as cohesion, the attraction between particles of the liquid. One particle in the liquid being attracted to another particle in the liquid. That's a cohesion. There's also adhesion. Adhesion refers to the attraction between particles of the liquid and other atoms or molecules that are surrounding the liquid. So a liquid particle attracted to perhaps the sides of the container. That's considered an adhesive force of attraction. We can see in this picture we have a blue liquid with glass stirring rods put into it, and if we look at the liquid where it touches the glass stirring rod, and you can see it blown up here to the side, there are attractions between the water molecules and the side of the container. Those are the adhesive forces at work there. But there are also attractive forces between the water molecules themselves, one water molecule and another, and that of course is cohesion. Surface tension is one of the special properties of a liquid that arise because of these forces of attraction. Since the surface of a liquid has no liquid particles above it, the particles at the surface cohere to the liquid below, and the surface exhibits a surface tension. This is depicted in the diagram in the lower right. You can see that the particles at the top have no attractive forces to liquid particles above them because there are no liquid particles above them. So you have attraction between particles across the surface, and you have attraction between those particles and the ones below them, but there's no upward attractive forces of cohesion. And that gives that surface tension across the top. Surface tension can cause a liquid to form spherical drops. In the spiderweb image, you can see these particles approaching a nearly spherical shape. In the upper picture, you can see water droplets beaded up on the surface of a waxed car. Now they have a flatter bottom because of gravity, but they do try to approximate a sphere. Low surface tension, such as what occurs in gasoline, causes drops to be more flat. There's not enough force to overcome gravitational pull. So as you can see in this lower diagram, the top picture is probably something with a strong attractive force, such as water. Water has a strong cohesive force pulling the particles together. The lower picture, you can see that the liquid droplet is nearly flat. That would be like gasoline or something with very low attractive forces acting between the liquid particles. Adhesive forces of attraction exist between water and the glass. That's that adhesion force, which is why water appears to try to climb the sides of a graduated cylinder, giving us that upward curve at the edge of a meniscus, as we see in this picture to the right. Viscosity is another property that all liquids possess. Some liquids are more viscous than others. It has to do with the cohesive forces within the liquid causing particles to be attracted to other nearby liquid particles. Stronger cohesive forces do not allow the particles to slide past each other as easily, and therefore there's more resistance to flow. We can see that in the picture to the right where we see the honey, which is a very viscous liquid. At the top picture we see what looks like 3 test tubes with water in them, but we can tell those don't all contain water, even though they're all clear liquids, because they were all tipped at the same time, yet they're pouring at different rates. The most viscous liquid is on the far right, and the one that flows the easiest is on the left. So viscosity is a resistance to flowing, and a viscous liquid is one that has a very large resistance to flowing, such as maple syrup or honey. Heating the liquid can cause particles to move faster. If they're moving faster, it's easier for them to overcome those cohesive attraction forces. And so there will be a decrease in the viscosity of a liquid, which is why you heat up your maple syrup before you put them on your pancakes in the morning, because it'll pour out more quickly from the container. It lowers its viscosity. We're going to look at liquid water from a large scale picture that we see here, and we're going to magnify it so we can see what's happening with the particles down at the molecular level. And so these particles in the liquid are in free-flowing motion. They do stay down within the liquid, and you can see every once in a while an attractive force occurring as particles come near each other. That was liquids. So we've finished talking about the special properties of liquids and what it takes to be classified as a liquid. But what about gases? That's our third state of matter that we have not studied yet. What does it take to be classified as a gas? Like a liquid, a gas takes the shape of its container, as we can see in the jar. However, we can also see in the jar that the gas has expanded to fill the volume of the container. Gases do not have a definite volume. They can take up more space or less space. Particles move faster than they do in solids or liquids, and they also possess the ability to flow, just like a liquid does. So they're not held in a fixed position. They have the ability to flow. So believe it or not, a gas is also considered to be a fluid, because all that a fluid is something that can flow. Now, in a gas, particles are usually much farther apart than the particles of a liquid, so gases are more easily compressed into a smaller volume. So gases are very highly compressible, liquids are only slightly compressible, and solids are considered essentially incompressible. The particles of a gas are moving so quickly and are so far apart that they don't usually interact with each other. As you can see here, once in a while they might collide with each other, but they bounce away so quickly they don't have time to experience much of a force of attraction between the particles. Gases are miscible with other gases in all proportions. Now, the word miscible means able to be mixed with. Gases will mix in any proportions. Gases behave differently from solids and liquids because of the amount of empty space between the gas particles. As I mentioned before, essentially, the particles do not interact with each other. And that's different from liquids and solids, where they're closely packed together and therefore experience a lot of attractive forces and repulsive forces possibly also between them. Now let's look at the behavior of a gas. We see here a liquid being heated, and above the container you would have gases forming. If we magnify this and look at it at the molecular level, we see water particles leaving the surface of the liquid to go out into a vapor phase. So they actually become gaseous, and they're now spaced so far apart that there's no interaction between them. So here we have a side-by-side comparison of our three states of matter: solid, liquid, and gas. As we can see, a solid holds its shape and has its own fixed volume. A liquid takes the shape of its container. It does have a free surface, meaning a surface that's not in contact with the container. That would be that top surface there. And it does have a fixed volume. Its volume is not changing. A gas, on the other hand, takes the shape of its container, also has the volume of its container, and does not have any free surface because on all sides it's contained by the container. We have three states of matter pictured here. So tell me, which of these is solid, which is liquid, and which is gas? There are several different clues that will tell you this. They're all being heated, but you can tell from the thermometer readings that some of them are heated to a higher temperature than others. We expect, if this is all the same substance, for the substance to be a solid at the lowest temperature, a liquid at the in-between temperature, and a gas at the higher temperature. So that would suggest that the center one is the solid, the one on the right is the liquid, and the one on the left would be the gas. But that's not the only way that we could tell. If the thermometer wasn't inserted, would we have enough information to determine solid, liquid, or gas? And the answer is yes. We can tell in the center that although some melting may be occurring, we do have a solid structure that has not taken the shape of its container fully. So the center one is a solid. Now on the right you can see the particles have spread out flat in its container as much as it could, but those particles are not bouncing around freely. It does have a free surface on its top side. And on the left we can see the particles are moving much faster. That's one hint that that's a gas. You also can tell that it is filling its container, which is another indicator that it is a gas. Many people use the terms gas and vapor interchangeably, but there is a difference. Gas is what we call a substance that exists in the gaseous phase at room temperature. But not all substances do that. For example, water does not normally exist as a gas at room temperature. Its normal state at room temperature is a liquid. So if water exists as a gas in your classroom at room temperature, then we would call this water vapor because it's not its normal state of matter for that temperature. So vapor refers to the gaseous state of a substance that's generally a liquid or a solid at room temperature. Remember physical and chemical changes? Well, looking at physical changes once again, physical changes affect one or more of a substance's physical properties. When matter undergoes a physical change, remember that no new substance is formed. However, the appearance of the matter may drastically change, as we see in this picture of the car being smashed by the wrecking ball. Most of the identifying properties will remain unchanged, and the content of the matter is still the same. It's still made up of metal and plastic and glass. It's just now in more of a shattered and bent up shape. Now, physical changes can be reversible, such as melting and freezing, boiling, or even dissolving, or they may be irreversible. When something gets crushed, that's an irreversible change, unless you take it through several other changes to try and get it back into a solid state. Tearing, I don't know about you, but I've never been able to tear a paper towel and then get it to seam itself back together and be one whole paper towel again. And breaking, same kind of thing. We might be able to glue something back together, but now we've added some other stuff in with it to try and get it held together. It's really not totally in the same physical shape. When sugar dissolves in water, a reversible physical change has occurred. Yes, I said that was a physical change because remember, it's still sugar water or a sugar solution. The sugar is still there and it's not chemically reacted with the water, it's merely mixed together. We can get that sugar back out if we just evaporate the liquid away. The sugar will recrystallize in the bottom of the container. Freezing, melting, vaporization, which is also boiling or evaporating, depending upon conditions, condensation, deposition, and sublimation are all physical changes that we refer to as changes of state. It's important that you understand which change of state is occurring. When a solid changes to a liquid, I think we all know that that's melting. And when a liquid changes to a solid, most of the time people can figure out that's freezing. You may or may not have heard of the word vaporization. But just think of vapor turning into a gas. Vaporization is the process of going from a liquid to a gas. Doing the reverse change of state, going from a gas back to a liquid, is not vaporization. It's called condensation. You have condensation form on the outside of a glass. On a hot summer day when you have a glass of ice water, you will frequently see liquid water from the atmosphere condense on the outsides of the cool container. The other two processes are a little less familiar to us. Solids going to a gas, gases going to a solid with no liquid phase involved. You heard me correctly, no liquid involved. When a solid changes directly to a gas, that process is known as sublimation. You may have seen that happen before. Maybe you made some ice cubes, put them in your freezer, forgot your ice cube trays or they got buried in there for months, and then you finally unbury them from the freezer and the ice cubes look a lot smaller than they did before. You begin to wonder, did I only half fill this ice tray? And the answer is no. Sublimation has occurred. The solid turned directly to a gas in your freezer. Deposition is going the other direction, where a gas becomes a solid with no liquid phase. Frost is an example of the process of deposition. Let's consider how changes of state are involved when a candle is burned. When you burn a candle, the burning part is a chemical change. That's not what we're here to talk about. We're talking about the heat produced as the wick is burned. That tends to do what to the wax? Well, if you've ever burned a candle, then you know that the wax melts. So it goes from a solid to a liquid. Why is it that we frequently smell scents, such as cinnamon, when scented candles are burned? Is that a chemical change going on? It's not. What happens is those scent particles have gone to a vapor In other words, they have become a gas and they have moved through the atmosphere to your nose to be detected. Hopefully now you understand a little bit more about the different phases of matter, solids, liquids, and gases, and the changes that occur as one state of matter changes into another.